Now we have talked about what differential equations are and how to solve them. But we are not talked so much about why do we want to solve them in the first place. And the reason for that is they have many real-world applications. For example, in natural science, engineering, economy. So we will see some examples of that now. Let y be the height of an object above the ground, and the object is falling freely to the ground, meaning that we disregard air resistance. Then it follows from physics that the object accelerates towards the ground with a constant acceleration of roughly 9.8 meters per square second. Since the object is falling to the ground, it means that acceleration is negative. If we calculate the height positive upwards. Acceleration is second derivative of height. So we have that the second derivative of y is equal to 9.8. If you take the antiderivative of this, we get the derivative of y. And here we get an integration constant. And if you take the antiderivative again, we get y. And now we must also take the antiderivative of this one, which is c times t. And we get a new integration constant. So we see that the height of the object above the ground as a function of time is given by this. So the solution to this differential equation is this one. If we now have some initial conditions, let's say for example the object was dropped at time 0 from 50 meters, and assume that the initial velocity was 0, meaning that it was dropped from rest. Then we can use those to find out what c and d must be. So let's take the first one. So we put 0 here, then this should be equal to 50. And on the other hand, we put in here, and here we have 4.9. And you see that this disappears and we have left d. So d must be 50. And we can find out c by using this initial condition here. So we put 0 here. This becomes equal to c. On the other hand, this is equal to 0. So we see that c must be equal to 0. So if you use c as 0 and d as 50 in this, you see that the solution to our differential equation, this one, is given by this. So this is the height of the object above the ground falling freely if you drop it from a height of 50 meters and with 0 velocity. Let n be the number of inhabitants in the country after t years. Then the derivative of n is the increase of number of inhabitants per year at time t. It's reasonable to assume that the increase in the number of people living in the country at some time is proportional to the number of people living in the country. So let's call that proportional factor k, and that means that it's proportional to n of t. Let's say that this is equal to 0.01. That means that the increase in number of people per year is 1% of the people living in that country. So we get this one. We have already seen that the general solution for an equation of this form is like this. To find out what c must be, let's assume that we have an initial condition that the number of people living there at year 0, if you start, for example, calculate the year 2000 as year 0, should be given as 1 million people. Then we have that and this is just equal to 1. So we get c equal to 1. And if you put that here, then we see that the solution to to this differential equation gives us the number of people living in the country after t years. So the starting population is 1 million, then it increases exponentially. Assume that we have some object with some temperature T at time small t, given in terms of degrees Celsius, for example, and T given in minutes. Then Newton's law of cooling. Newton's law of cooling says that the temperature change per time unit, that is the derivative of T, is proportional to the temperature difference of the object and the room temperature. This means that the higher the temperature of the object in relation to the room temperature, the faster it will cool. And when it approaches room temperature, the cooling will go slower and slower towards room temperature. Let us now solve this one for some initial conditions. So let's say we have a cup of coffee here and its starting temperature is 80 degrees Celsius. And that after 5 minutes, the temperature has cooled to 40 degrees Celsius. If we multiply in K here, we will get this equation. And if we move this over to the other side, then we get this differential equation. And this is the first order differential equation, because here we have the unknown function t, and we have derivative of first order. And here we have a function of t, in this case just a constant. And here we have another function, g of t. Using the general solutions formula for differential equations of first order was given by this. And if you have forgotten about the formula, you can check up here how we deduced it. Now f of t is just the antiderivative of this constant here. So that's just kt. G of t was just this constant that we put here. And here we have the antiderivative again. Here we have a constant that we can take in front. The antiderivative of this one is the same, but we have to divide it by the inner derivative. And then we also have integration constant. And here we have to remember to multiply both of them. So if you first multiply in here, we see that the k's will cancel and the exponential will cancel. We are only left with the room temperature. And here and then we get this one. So the solution is given by this one. Now we have some unknown constants, C and K. TR, the room temperature, we have to decide on. So let's say that's 20 degrees Celsius. So we get this function. Using the initial condition, then the temperature at time 0 should be 80. And then we put 0 here. Then this just becomes 1. And if we subtract 20 on both sides, then we can solve for one of the unknown constants. So let's solve for C. So we just get this one. So if we substitute C here, then C times K just becomes 3. So the temperature is given by this. And to find out what K is, we have to use the second initial condition. So if we have put in 5, T equal to 5, then this should be 40. And put in 5 here. Then we can remove 20 on both sides. Then we get this equation. And before we continue, just we tidy up here now to make room and just write up so far we have gotten with the function. And here we now need to divide with 60 on both sides. We get the third here. If you take the natural logarithm on both sides, then we see that this becomes ln1 minus ln3 due to one of the logarithmic rules for division. And this here just ln and e cancel. So if you're unsure about these things, you have to repeat your logarithms. This is just now 0. So this is minus ln3. So we see that k is equal to ln3 divided by 5. And using calculator, this is roughly equal to 0.22. And then we can put that in here. And we have finally arrived at our solution. So we see that the temperature of the coffee decreases exponentially with time, from 80 degrees down to 20 degrees.